Now, there are actually three classes of these stellar engines. The first class, or Class A, titled the Shadkov Thruster, is a propulsion-based system that consists of an enormous mirror light sail, which is a statite, and that's an artificial satellite that employs a solar sail to continuously modify its orbit in ways that gravity alone would not allow. So this sort of, it's sort of like putting a parachute to something, and then a jetpack would basically, propulsion.
Which we have right now, actually. They just recently, over the last couple of years, and it's up there right now. It's hasn't crashed and burned or anything. It doesn't do much. It just kind of hangs out. But it's the Light Sail. I think it's the Light Sail 2 or whatever they called it, because the first one was more of a test thing and it didn't go very far. But the second one, it's run by I think the SETI Institute and the Planetary Society, which are two groups that look for extraterrestrial or different things out in the universe. So they have a light sail out there in space right now as we speak. It's small, it's not that big, but it's a start. So the technology for that kind of thing is something that's actually around right now, which is pretty exciting.
Yeah, I'll be interested to see how they I'll be interested to see how they do that in the future, because these are like serious business. Like, it's one thing to have like one thing of it. It's like another thing to put it in essence. Right.
Yeah, it's more proof of concept that it can be done. Now, it's like you said, whether we'll be able to do something real big and massive and like really incredible with it, who knows? But it's interesting that we've been able to make the technology work to some extent.
It's just really expensive, and the energy required is something we don't have the output to produce at the present time. So there lies a problem. But it would be classified as a megastructure, and what it would do is it would balance gravitational attraction towards and radiation away from the star. Now, the radiation pressure from the star itself is asymmetrical. This means that the radiation is being emitted in one direction. Now, this excess pressure acts as a net thrust and accelerates the star in the direction of the hovering statite. The speed at which it would be moved would be very slow. So, like, I know people probably think, oh, it's going to be fast. No, we're talking like 10 million years. To break down a little bit of the math for you guys, it would take roughly 1 million years for a star such as the Sun, with a luminosity of 3.85 times 1026 W and mass of 1.99 times 1030 kilograms. The total thrust produced by reflecting half of the solar output would be 1.28 times 1118 N. And after a period of 1 million years, this would yield an imparted speed of 20, I'm gonna see, I think this is like 20, it's M-S, I forget what that means, I looked this up earlier, sorry. With a displacement from the original position of roughly 0.03 light years. After 1 billion years, the speed would be 20 kilometers per second. Oh, so it'd be probably 20 meters a second. 20 kilometers per second, and the displacement of 34,000 light years, which is a little over a third of the estimated width of the Milky Galaxy. Now, some of this is going to be very, sort of heavy. I tried to leave a little bit of the math in and leave some of it out because I know our listeners don't want to be bored and bogged down with a lot of the more number-esque parts of this. You can look this stuff up online. There's a lot of really useful mathematical information behind it. Like what you heard? Well, head on over to www.spreaker.com/user/ThisUncannyEarth to hear more from this episode 152, Dyson Spheres and Stellar Engines, and to hear more episodes of This Uncanny Earth. As always, why be boring when you can be uncanny?